Okay, it'll take me a minute anyway. I don't want to take too much of Mukund's time, but he can go a few minutes late anyway. So hi everybody. It seems like the first week of TASI has been going pretty well. I hope everyone's been enjoying the lectures. Tom was already talking a little bit about student talks, which is something that the students traditionally do, and some people have volunteered to sort of spearhead that. So the other thing that we want to call your attention to that you can do is it's traditional to make a TASI t-shirt. So I have some pictures here. I don't have a picture of the 2020. This is what I had hanging in my closet. But this is the TASI 2019 t-shirt. Tom is actually wearing it. Tom Faulkner is actually wearing it right now. You can see the front and the back. They traditionally say TASI and usually the year on them, and have some inside jokes. You know, there's a thermofield bagel here. You can only imagine what they were talking about. Let me see. Here was TASI 2018, which was a more phenomenological one. You've got some sort of Street Fighter thing with theory versus data going on here on the back. This is one of my personal favorites, TASI 2017. A non-physics friend of mine said to me that they had long dreamed of having a t-shirt that had a snail riding on a watermelon throwing up the moon. This was 2017. And then I was also, just my last example, going to share for you. So this is TASI 1999, when Mukund and Veronica and I were at TASI. It's got the little M on the back, and you never know. Sometimes these t-shirts they're hot stuff, and sometimes you show up at a conference and you just never know when someone is going to be wearing the same thing as you. So this can happen. So, but it is, if there is going to be a TASI 2021 t-shirt, and there should be, then it's up to you all. So it is traditionally the students who design the shirt, what's going to go on the front, what's going to go on the back. Last year, people found basically a t-shirt making company on the internet that would make them, and sort of got all the sizes and all that organized. So I would say, if you think you might like to sort of spearhead this, talk to one of the organizers. I think it would be good. I mean, you could do it all on your own, but I think it'd be good just to have us know that there was someone who was in charge of it, so we would know that it was being taken care of. So if you think you might like to lead the t-shirt design, just let one of the organizers know. And it's sort of a nice traditional part of TASI. Maybe if you like, I can put these pictures on the wiki for inspiration, or on Slack for inspiration. So I guess that's what I want to say. Any of the other organizers want to add anything about t-shirts?
Yes. Fun exercise. We even had a little bit of a competition in our year of multiple sets of students designing something, and then there was a vote on what is the most fun picture.
And this is a great shirt. I've still got it 22 years later. Okay, well, I guess I will stop here and let Veronica introduce Mukund.
All right, so welcome all back for the last lecture of this week, which is Mukund's 5th lecture. After that, we will have the Q&A. Okay, so take it away, Mukund.
All right, thanks. And so I ended yesterday talking about computations of entropy from the Euclidean path integral point of view. And now I want to sort of use that to segue you back into discussions. Did people hear me before, or did I get spontaneously muted and unmuted?
You got muted a moment ago.
Just for like a second. Okay,
great. So let me remind ourselves where we were. We were trying to talk about the, we discussed the global black hole, and then I talked about the planar limit, where the black hole in the short shell black hole in AdS has a horizon size that's macroscopically larger than the AdS length scale, and you get a solution which is basically the solution where the boundary is now a copy of Minkowski spacetime. So I wrote up something here to explain the computation of the free energy explicitly, which I'll put up later. But what I want to do now is to talk about interpreting this geometry in the Lorentz image. I've written out the solution here, and this function f is basically this in d dimensions. It's a simple harmonic function. And if I look at the solution in its maximal analytic continuation as a Lorentzian manifold, then what I find is the eternal AdS Schwarzschild black hole solution, where we have two boundaries, two asymptotic boundaries, which I've called the left and right, respectively, which are separated by causal horizons. In this case, the causal horizons is just the event horizons of the black hole. And the solution has a singularity, which in these coordinates is at r equals 0. The horizon, of course, is at r equals r plus. And if you look at a time slice, cutting across the Penrose diagram, then the geometry on this time slice looks like a spatial wormhole. So I'll just draw this as if the space was compact. Where the neck is basically of size r plus. There are many ways to interpret this, but one way which I like is to think about the Euclidean solution and realize that the Euclidean solution computed for us the partition function so I can interpret that partition function as the inner product between a bra and a ket if I happen to have a moment of time reflection symmetry, so that I can cut open this path integral and think of it as an inner product. And in this case, I do, because the solution is globally has a time translational symmetry, so I do have an involution. And so I can cut the solution, I can take the solution, which is the Euclidean solution in the past, cut it open halfway through, let's say at t equals 0. This is the same slice as the slice here. And then, as we were discussing yesterday, evolve the data I get of the geometry. So what I would get if I cut open the Euclidean solution at t equals 0 is I'd get a metric, a spatial metric, which would satisfy Einstein's constraints equations. Okay, so I'd get a spatial metric and a spatial extrinsic curvature, which I can compute. And that can be evolved with respect to the gravitational Hamiltonian forward in time. And that evolution will reproduce for you the future half of this Penrose diagram, future half with respect to this global time coordinate running up along the Penrose diagram. And there's a fixed point of this time translational of this d by dt killing symmetry, which from the point of view of the Euclidean solution is just the center of the disk. But from the point of view of the Lorentzian solution is a bifurcation surface on the event horizon. So there are two ways to interpret this, and we can ask what state do we get when we cut open the Euclidean path integral. And the state we get is a thermophile double state, as Oliver was just showing us in his bagel. This time it's not a bagel, it's just a sandwich. They're just two copies of flat space on both sides. And I've written this out in a finite dimensional quantum system as the sort of the state, which is where I've paired up energy eigenstates for two copies with a Boltzmann factor and a normalization by the partition function, so that when I trace over one copy, let's say the left set of fields, I get back the thermal density operator on the right system. So this leads to the identification that the eternal black hole geometry corresponds to thermophile double state. And moreover, in this way of thinking about it, the black hole entropy that we computed yesterday by using the Bekenstein-Hawking formula which is the area of the surface divided in units of in Planck units, can be also interpreted to be the von Neumann entropy of this density operator after tracing out the left set of degrees of freedom. Okay. So from geometry, this is pretty clear that what you get from the Euclidean construction is a two-sided black hole, which has the characteristics of a spatial wormhole, and the thermal entropy can be interpreted as the von Neumann entropy between the two systems that make up the thermophile double state. So most of you probably have seen this, but I just want to use this to motivate, for now, the holographic entanglement entropy proposals by Jutta Kainagi and follow-ups thereof. Because in this simple, this is not historically how it was motivated, but I think it's a good mnemonic to try to understand the constructions. Because we got the von Neumann entropy geometrically as the area of the bifurcation surface, one could postulate more generally that the von Neumann entropy for some subregion on the boundary could be viewed as the area of some surface in Planck units. The question then becomes, what characteristics should the surface satisfy? And the proposals basically say that at leading order in G Newton, this surface must be an extremal surface which is homologous to the region whose entropy you're trying to compute on the boundary. Okay, so if you have a region A on the boundary, then the surface E is extremal in the sense that it's a local extremum of the area functional in Lorentz signature geometry. If there are multiple such surfaces which satisfy the local extremality condition and the homology condition, then one takes a global minimum in the space of solutions. So for example, we could have the region A being in global AdS being two disconnected, composed of two disconnected pieces. Then there are two different potential solutions to the extremal surface. One is this pair of extremal surfaces. The other is this pair of extremal surfaces. And depending on the relative size of the region A to the boundary circle, the phase transition between them is very analogous to the Hawking-Page phase transition we saw for the black hole in our discussion yesterday. In fact, if we were computing not the von Neumann entropy, but rather the second Renyi entropy for the system in 2 dimensions, it would be exactly the Hawking-Page transitions in that context. You could also have more exotic scenarios where you have the region A straddling, say, on one side of on one boundary of this thermophile double state on the eternal black hole. So I've just drawn it. Now, by looking at this picture top down and excising a disk of radius r plus, so that it looks like a black hole. And I'm taking a region A that's sort of on this boundary of some size. Then, depending on what size this region A is, I can have an extremal surface that either is homologous to it, but then goes on one side of this black hole, or I can have an extremal surface that sort of is a disjoint union of the surface that's on the other side and the black hole horizon itself. And again, you can have a transition between these two configurations depending on what the relative size of this region A is relative to the entire boundary. So I just wanted to flash this for now, because this is something that Engelhardt will talk about in greater detail next week. I just wanted to use the excuse of talking about thermal states to motivate the holographic entanglement entropy prescriptions. Good. Let me pause here for a moment to check if there are questions, and then switch gears to talking about something else.
I have a question.
Go ahead.
So between the time where you have the disjoint union and the one where you don't. If I imagine it as you compute for A, then you increase A, I guess for some bulk space-time, like, could I imagine that it will, like, there's like a discontinuous jump? Because as you increase A, I imagine that it will become, what's it called, disjoint at some size A as you increase the area on the boundary.
Yeah, so in all these examples, the way I'm thinking about it is I'm fixing the region, I'm fixing a moment of time because the entropies are computed at a fixed time. So SA is basically the von Neumann entropy of a density operator. And let's say we're computing it at time t, we'll just compute the density operator at that time. So you tell me what region you want. I'll take the global state in the theory and trace out the complementary region and compute rho A. So trying to explore how the von Neumann entropy changes as a functional of the region size, that's an exercise that samples over density operators. Right? We're not changing dynamics, we're not changing temporal dynamics, we're not looking at this as a function of time. So that said, we could certainly ask that question that you just asked, which is, as I vary the size of A, how does this von Neumann entropy track? For small sizes, it will sort of follow this connected surface, because for small sizes for any state, it doesn't really matter. It's mostly like it's a surface that's very close to the boundary, and it will look like the usual AdS calculation. As the size gets big, it starts seeing the details of what the state is, the global state is doing in the interior. And I could say this many different ways, but let me say this slightly from a non-field theory point of view for a second. Usually, the solutions in the interior have a gravitational potential. Right? So you can think of a gravitational redshift as you go into the interior, which is accentuated by both the AdS curvature and the matter that you put in to make the solution. The extremal surfaces typically they want to minimize they want to try to globally extremize their area. But one thing they want to do that is to, if it are purely spatial, they would just want to minimize their area. The reason they have to extremize their area is they have to also wiggle out in time, and they can't just purely minimize their area. They can be in time. But a corollary of this process is that they don't really want to be in regions of large redshift. So they try to avoid regions of large redshift. And what can happen is one of two things. You can either have solutions that stay connected no matter how big the region is. It can also happen, and it does happen actually for global Schwarzschild black holes in higher dimensions, in dimensions 4 and higher, that past a certain critical size, a connected surface just doesn't exist. Okay, because the surface doesn't want to penetrate. It doesn't want to sort of bend back down and go around and come back, because that's not going to minimize it or minimize or extremize this area. In that case, the only thing that you end up having are the disconnected surfaces. However, whenever the transition happens, these transitions are first order. So there's a locus where there are two possible solutions which are of the equal area. So this is very clear, for example, in this case, where there exists a critical boundary size, which depends on the space-time dimensions, when these two, the sum of areas of these two surfaces equals the sum of area of these two surfaces. And past that critical value, one or the other is dominant. Now, this is statement that's true to leading order in G Newton, and the statement that's true for the von Neumann entropy. I'll for now, not discuss what happens to any entropies where also such space transition happen. But there it's a because that's a statement about different geometries. Does that help? Right.
Excuse me, just a quick to make sure I understood. In your top left figure, the horizon of the black hole is part of the Rio-Takayama surface, right?
Correct.
Okay, thank you.
Correct. Yeah. So when I say disconnected, I mean that the surface is this plus this.
Sorry, can I ask a question?
Go ahead.
Sorry. Okay. Well, so I was wondering, is it possible to have a discontinuous change in the area from RT under a continuous change of the geometry or of the boundary region that you pick?
I don't think so. I thought some of us gave an argument. Maybe Veronica can remind me that it doesn't happen.
So in RT, it doesn't happen almost by construction. You have multiple families that exchange dominance, and whichever one has, so if you plot the area versus some parameter that you're changing smoothly, some family exchanges dominance with some other family, and that the dominance exchange point, by definition, they have the same area. That's for the RT prescription. If you have in HRD prescription, if you have time dependence, it's not a priori clear that you can't have discontinuous jump. I guess that's what Marcus was also asking. So that argument is much less clean, but we believe that it is the case that the areas still match on, that you're not going to have a gap. Okay, but that argument is much harder to make.
So I guess in principle, some extremal surface could pop into existence with a minimal surface, with a surface area that is smaller, and that could potentially spoil continuity.
Logically, yes, and we don't know of any example of that. And I likewise am forgetting the argument, so I should remind myself how far we went in that route. But
I think I agree with you that we made the argument only for RT.
Where it's very straightforward.
Very straightforward. Thanks.
Thank you.
A follow-up on that question is, in the case where you consider this generalized entropy prescription, in that case, it doesn't matter only the area, you also have the entanglement entropy of the, let's say, entanglement wedge. To that. So in that case, can you have discontinuity of extremal surface area, right? Like you don't have a discontinuity in the generalized entropy in that case, but you have a discontinuity on the area of the RT surfaces. Is there?
Yes, because you say that it's just a sum that needs to be that needs to agree at the transition point, but not independently of the pieces. That's probably true. That's a good point. Yeah. Sure.
Sorry, just one question. In the previous slide, you had the entropy that's equal to the area of the bifurcation surface. Is that understood also in an RT sense? Like, is the bifurcation surface minimized? Or yes, I don't see how it is homologous to the full boundary, or maybe it's just completely disconnected, not related to it.
No, it is homologous to the full boundary because it's completely it's a full boundary. So let's draw the spatial section. So this surface is homologous to this boundary. Okay.
Oh, okay.
So in homology sense, it works. Going back, it is a global. It's actually a minimal area surface. Because on this slice it's minimal because it's a neck, but it actually also minimizes. It's also a local extremum because if you increase the if you try to go up, it doesn't. It's a local size.
Maximizes it in the time direction.
In the time direction.
Minimizes it in the spatial direction.
Okay, thank you.
So I didn't write the formula for. Sorry.
Go
ahead.
So I was wondering, in that minimization, you take the one with the smallest area, but in the case of, I think in one of your papers you showed there could be infinitely many candidate surfaces given the same boundary region. Is it clear why that infinity doesn't sum up, and therefore you can't really take the smallest one?
I'll try to give a path-integral argument for it. It's not a very satisfactory argument, but it's an argument that I learned from I think Don Merolf. So if you have multiple saddles, then let me write them as this. Get some determinant. And okay, this argument would be even sharper if I use the Lefkowitz-Maldacena construction, which wasn't planning to talk about, but I'm happy to discuss it if people are interested. The way Lefkowitz-Maldacena construction works is to basically let me say it in words and not try to explain that just in real time and take it over in discussion. What they try to do is they try to give a local version of the Gibbons-Hawking argument. So they try to do Euclidean construction, where they try to compute not trace rho log rho, they try to compute trace rho to the n. And this, they argue, can be computed by doing Euclidean gravity with a conical defect. This is the part I'm not explaining right now, of strength proportional to n-1, of tension proportional to n-1. Now, if you now we just follow the rules of Euclidean quantum gravity and try to compute saddles and compute the action on the saddles like we did for the free energy of black holes. And what you would get is you'd get contributions which look like this. If you have multiple saddles. Now, to get the von Neumann entropy from trace rho to the n, you want to divide this by 1 over 1 minus n, and then take the limit n goes to 1. In that limit, if you look at this formula, there's a question of how you take that limit n goes to 1. Because this formula was arrived by assuming saddle point was valid. By assuming that C effective was large, so that I could actually evaluate the quantum gravity path integral by doing saddle point. But strictly speaking, C effective times n-1 is a saddle point parameter. So I have a problem that unless I take C effective to infinity first, followed by taking n to 1, I'm not actually taking the saddle point limit. If I take n to 1 first, while leaving C effective fixed, I'm not even in the saddle point regime. So the kind of situation that you're wondering about, Jan, is when you have multiple saddles, they will all show up when you're trying to compute, I think when you try to compute NEs. And different ones could dominate there. But as you take n to 1, if you take the limit n to 1 after taking the limit C effective to infinity, one of them just straight up dominates.
Okay, that I think that makes sense. But one step there that's slightly unsatisfying is, why do we believe a saddle point is good in the first place?
Okay, this is $1 million question. This I don't know a good answer to, and many people have complained about the Euclidean quantum gravity path integral, and the rule seems to be we use it, and when we get results we like, we say it works, and when we get results we don't like, we say it doesn't work. There should be a better story to tell, and I think the better story to tell is really asking what contour should the Euclidean quantum gravity path integral be defined on? What is the contour of integration? For simple problems like, for like computing the black hole entropy like we did here, it's more or less clear. And there are many interesting calculations that I didn't say, that not only can you get the leading corrections, for example, from leading Bekenstein-Hawking entropy from this calculation, but you can also get the determinant calculations done correctly. And there have been interesting matches with, for example, in the M2 brain case, people have computed this and shown that it matches very nicely with the expectation from field theory and so on and so forth. It's just that in more interesting contexts, we don't seem to have good anchors on how to make sharp the argument that we should trust the Euclidean quantum gravity path integral. So if you want my take on it, this is something I want to talk about. I think the right take is that what we really should do is we should understand the Lorentzian quantum gravity path integral. And the saddle point basically we should understand how to take stationary points of the path integral, and in that process learn where the Euclidean saddles contribute. But I don't think we have the tools. I mean, we have the tools, we don't have some of them are technically challenging to understand in great detail.
I see.
And I'll say
Thank
few more things about the disconnect between Euclidean and Lorentzian computations as I go along today.
Okay, thank you.
Anything else, folks? All right. So that's all I want to say about entropies, partly because Neta is mainly going to focus on this. She's going to work through. She told me that she's going to explain to you various proposals for computing entropies from gravity and what they imply and so on and so forth next week. So then let me change gear and talk about real-time dynamics. Okay. So far, I didn't really talk about real-time dynamics. I told you that I sort of switched gears very early on to talk about the Euclidean quantum gravity problem and trying to even set up the dictionary between bulk and boundary data in terms of Euclidean dictionary. But I did say yesterday that when we go to Lorentz signature, there are normalizable modes that are not present in the Euclidean problem. So now let me ask the following question. Suppose you want to do the following physical experiment. You take a CFT, you add to it a perturbation, let's say some source times some operator. And now you really want the causal response of adding this source to your theory. So as people are asking in earlier discussions, I have my CFT, and let's say I have this eternal black hole. At this time, I turn on an excitation. How does the system respond? And the short answer is the system has to respond causally. So there should be a causal Green's function that tells me what the expectation value of the corresponding operator is as a functional of the source. And there should be a retarded Green's function that's purely supported in the causal feature of my source. And the retarded Green's function is easy to state. It's basically the expectation value of the commutator, which by construction vanishes for space-like separated points, with a time ordering step function to make sure that we're looking to the causal future of when the operator was inserted. So we'd like to compute these causal propagators, and our usual trick is to compute the Euclidean correlator and then do an I epsilon prescription to pick it out. Okay, so we can get this if you have full analytic control of your Green's functions. You can just get them by doing analytic continuation. So, for example, in the vacuum, we got a CFT correlator between 2 points in Euclidean space to be 1 over x minus y to the 2 delta. And you can write this out in Lorentz signature, and you realize that there's a question, this correlator makes sense when x and y are space-like separated, but when x and y are null separated, there's a branch cut to go from the space-like region to the time-like region. You have to analytically continue to the cut. But just picking up the discontinuity through the cut, you can define, and with an I-epsilon prescription, you can define the retired Green's function of two CFT operators in the matrix. For the discussion of bulk, I'm actually going to not talk about the vacuum, certainly not the Poincare vacuum, because the Poincare vacuum has subtleties dealing with Poincare horizons. And I'd rather talk directly about computing these kind of observables, the retired Green's functions, in the case when in the thermal state. Okay, and I'll show you that there's some interesting physics to be learned there, and interpret them from the point of view of a strongly coupled field theory plasma. So I'll start by first talking about the linearized problem. So I'll just talk about taking the CFT, and we can still stick to this eternal black hole picture, and turning on some source and watching the response of what's happened. What we learned from our previous exercise is that this black hole geometry should be thought of as providing for us some kind of thermal boundary conditions for our field theory. Right? It's giving us a thermal density matrix, but this is a field theory sitting at finite temperature. So you can imagine what you have is a thermal plasma of the fields that make up your boundary field theory. And turning on a source here is like coming to that plasma and pinging it. And what we're trying to measure is a response of what that ping does. Okay, so this problem is easy to set up in the linearized gravity. So what you do is you again solve the wave equation, but now remember that we have normalizable modes out here. The only thing we're going to do is if you want to compute this Green's function should be computed with boundary conditions where the source is turned on at the boundary point, and I need some interior boundary conditions which replace some kind of smoothness statement in the bulk. So what boundary condition should I use? Physically, from the Lorentzian black hole point of view, I have a horizon in the future, and since I'm in the eternal black hole, I also have a horizon in the past. Now, if stuff were coming out of this past horizon at me, if there was stuff coming out from the past horizon at me, then I'm not really talking about the CFT because I have stuff pinging into my CFT from somewhere else. All I want to do is I want my source to excite stuff and fall into the future horizon. So the boundary conditions for this problem are that I have appropriate normalizability at the boundary and future ingoing boundary conditions for the modes. This is easy to analyze. If you basically switch from the Schwarzschild coordinates I had in my previous slide to ingoing coordinates, which are regular through the future horizon, so they will cover this part of the Penrose diagram. So I've just changed from T to T plus T to V, where V is T plus R star, the tortoise, where R star is the tortoise coordinate. So now I try to solve the wave equation that I had before with future infalling boundary conditions and ask what class of modes do I have? But you see, this is no longer a closed system, because from a point of view of thinking about the bulk wave operator, the Schrodinger operator, there's some boundary condition here, which is fine, but there's a boundary condition on this end, which just allows probability to leak through the future horizon. So it's not a Hermitian problem. So you should expect real eigenvalues. And indeed, what you find are complex eigenvalues, which are the quasi-normal modes of the black hole. And I'll translate that statement into the analytic structure of the Green's function and show you what the analytic function structure of the Green's function looks like. This is for a generic operator, and I'll say a few words about some special class of operators in the sequel. So I Fourier transformed the Green's function to frequency and position domain. I'm still on flat space, so I've just taken g omega k to be e to the minus I omega t plus ik dot x g x. That's it, t comma x. So remarkably, you find in AdS that the Green's function only has poles, and the retired Green's function only has poles in the lower half complex omega plane. The location of the poles depends on the horizon size and the dimension of the operator and the wave number. But for a generic operator with some non-trivial conformal dimension, roughly speaking, the separation from the imaginary part is of order the horizon size or the temperature. This is not an exact statement, but a gap between the horizontal axis and the first the mode with the smallest imaginary part is of order the thermal scale, which makes sense. Is a conformal system on flat space. So there's only one scale in the problem, which is the temperature. And so the leading behavior, the gap is basically set by the thermal scale in the problem. But it's not just one mode. You have an infinite sequence of modes, which are the locations of which depend on the details of the problem you study, but they can be computed in most cases numerically, or in some special cases analytically, and you can see these quasi-normal modes showing up in this Green's function. Let me say that this is very different in structure from the nature of thermal Green's functions for free field theories. Thermal Green's functions in free field theories have branch cuts. They have branch cuts because in free fields, once you have enough excitations, you can excite multi-particle states. So you actually have a cut running like a typical cut you have like in an S matrix amplitude when you see the multi-particle threshold. That doesn't happen in many examples of AdS CFT because the black hole solution, which gives you the dual Green's function, has strong coupling, seems to only have poles. There are some examples, typically to do with near extremal or extremal black holes, where you do have cuts. But they come purely because the extremal black holes have an internal infinity and the cuts run along the imaginary frequency direction. Okay. So that's the general story for generic operators but there's something very special about the class of operators that are dual to conserved currents. Okay. So if you look at if you have charge conservation, if you have a vector field in the bulk, then as we said, the vector field is dual to a conserved charge, or if you have energy momentum, then the energy momentum tensor is conserved. And this has implications for the structure of the quasi-normal modes. So let me explain what happens. So I've tried to make a particular parameterization of my wave vector. So I've picked some direction in the boundary and aligned the wave vector to that direction. And there's a plane, there's a space perpendicular to that wave vector. Okay, so I'll decompose all my vectors and tensors in rotation along the, depending on the transformation, in rotations on the plane orthogonal to the wave vector. Okay, this is convenient because it tells you what are the sort of modes that are special, and it disambiguates modes from the full multiplet of the current or the distance. So I've split the current into a longitudinal part and a transverse part, and longitudinal and transverse means whether they're aligned to the wave vector or they lie in the plane perpendicular to the wave vector. For the energy momentum tensor, it's a spin 2 object, so I have to split it up into a transverse traceless spin 2 part, a vector part, and a scalar part. Okay, and I'm just going to call this vector part the shear part and the scalar part the sound part, and you'll see why. What is special about these guys? The special feature is the fact that they have conservation. Now, if you try to counter a system which has conservation law and ping it with an external source, well, the system will want to settle down, the plasma will want to settle back down, but it can't really do so in short order because the conservation prevents the global Gauss law constraint prevents something from going on. It can't just decay back to where it was. So what really happens in the systems is that if you ping the charge mode, then the charge will try to relax back, but it relaxes back very slowly by diffusing. If you try to ping a plasma with a source of energy momentum, momentum will diffuse very slowly, but at the same time also produce a phonon mode, which propagates at a characteristic speed with attenuation. So this term is the sound speed, and this term is basically the attenuation of sound because the sound will eventually die out in the plasma. And there are coefficients here which tell you about the damping rate for the modes. But what I want you to notice is that all these modes have a frequency that scales with some power of the wave number, which means at zero momentum, these frequencies are going to zero. In my picture of the quasi-normal mode plot, what it means is that unlike typical operators where the modes were gapped from the horizontal axis, I now have modes that are close to the horizontal axis. I have modes close to the origin. And these are the long-lived modes that survive in a plasma because of conservation. So the charge diffusion mode, the coefficient here is basically related to the ohmic conductivity of a charged plasma. The momentum diffusion mode is related to the shear viscosity. In fact, the diffusion constant there is the shear viscosity divided by energy density plus pressure. The sound speed in conformal plasmas is completely fixed by scale invariance to be 1 over square root d minus 1. Because the equation of state is epsilon equals d minus 1p. We saw this from this you can get from the fact that the entropy is proportional to, or the free energy satisfies Stefan Boltzmann law. So free energy basically gives you the pressure, but then there's a TS term that gives you energy, and that's a factor of d minus 1. And this fact was noticed very early on and led to a very famous statement that was understood by, was just conjectured by Koptunson and Starinets, that if you look at the momentum diffusion rate and compute the shear viscosity, if you divide that shear viscosity by entropy density, then you get a universal answer for black holes in AdS, independent of dimension, in Einstein-Hilbert gravity, which is just 1 over 4 pi. So this led people, so this number was interesting because first of all, this ratio was typically much larger by a factor of 10 for most plasmas or most fluids. But more importantly, for QCD plasma, near deconfinement temperature, heavy ion collisions indicate that eta over S is of order some factor, 1 or 2 divided by 4 pi. So people were very excited for a while to think that maybe one could use holography to model strongly coupled plasmas. And this led to a lot of discussion in the context of modeling QCD dynamics or more generally condensed matter systems from AdS CFT. So this was discussed partly in John McGreevy's lectures from TASI 2015, and they're discussed in other places. So I won't go through much of the detail, but I'll just highlight this classic calculation in this context. Again, to connect back to something I said at the very beginning, this is one example of a quantity that's universal across a range of field theories in 4 dimensions, or let's say, or in any dimension. But especially if you look at 4-dimensional conformal field theories that have duals in AdS, we're only looking at graviton dynamics to obtain this coefficient. So it's purely restricting to the energy momentum tensor sector of the theory. It doesn't care what the other operators are. So it doesn't care about the OPE data of the theory. It doesn't care about the spectrum of the theory with respect to other operators. So this is some special feature coming out of consistent truncations in supergravity, that you can isolate and extract from just the energy momentum tensor some of these features. What I've described so far is basically extracting just the right amount of data to obtain the quasi-normal modes. I won't go through the details of how one computes real-time correlation functions from AdS CFT. This has a rich and storied history. I think we're starting to understand this much better these days, but the short answer is they're not computed in geometries of this kind, but in some side, they're not actually computed in the eternal black hole geometry, but I won't go through and describe for you because I want to say a few other things in the remaining 15 minutes. But related to the earlier question, I think trying to understand how such real-time computations are done is for correlation functions, I find personally helpful for addressing questions of the kind that were asked about, what saddles you should take into account in Euclidean quantum gravity, etc. Because these are physical quantities and they should satisfy definite causality properties, which are much cleaner in the Lorentzian context than in the Euclidean context. Let me pause here to check if there are any questions before I proceed to something else.
Sorry, I have a question. Will there be 1 over C effective correction to the ratio eta over S?
There will be. Those 1 over C effective corrections will come from, so there'll be many corrections here. So this quantity is computed strictly at large lambda and large C effective. In the ratio, C effective disappears, but each of eta and S are of order C effective. S is of order C effective because that's what we got from the bulk. This is, let's say, S for n equals for super angles. Eta is also proportional to T cubed. It's also proportional to n squared, and volume. The rest of factors are what matter to give you the 1 over 4 pi. But so you have corrections both in 1 over powers of lambda. So those have been computed because those people tried modeling by trying to think of higher derivative corrections to gravity and trying to think of effective models of gravity coming from string theory and computing 1 over root lambda corrections here. see effective corrections. There's an attempt to compute them, but I don't think it's as well understood because this has to do with bulk loop effects, as we've discussed before. Anything else? Okay. So these statements were about linear response, but I wanted to say a few words about going beyond linear response. But this was just pinging the plasma and seeing what happens if you sort of ping it. And the general problem is basically a numerical gravity problem, which is of the kind that we were discussing yesterday. So let me draw that again. So the general problem basically says you start off with initial conditions for the state in the bulk. And then you turn on sources on the boundary, which propagate in. And then you numerically evolve Einstein's equations with appropriate matter with these initial conditions and these supplied boundary conditions for when you're turning on sources and so on. There's been quite a lot of interesting progress in developing numerical schemes, especially characteristic methods to solve such numerical problems. I can put a reference to a review from 6 years ago for those of you interested by Chesler and Yaffe on trying to do such kind of numerical trying to study numerical relativity to understand properties of strongly coupled systems. But there's one context which I wanted to highlight where you can understand the system analytically, and that's for simplicity. Let me just focus on these two modes of the energy momentum current. So what I told you is that when you look at the energy momentum tensor, if you look at gravitons, there are two quasi-normal modes, or rather a pair of quasi-normal modes for sound and a single mode for shear, which are special in that they live in their domain of support is small frequencies and small momentum. So you could imagine the following. You could imagine trying to construct an effective field theory that somehow integrates out all these heavy quasi-normal modes and just focuses on the light quasi-normal modes that are long-lived. Okay. What would such a theory be? Well, that theory only knows about conservation, and it only knows about the physics of sound and diffusion sound propagation and momentum diffusion. But we know what such a theory must be. That such a theory must just be hydrodynamics. Okay, so it's a sort of global description of the statistical description of the plasma viewed as a hydrodynamical system. So how does gravity know about this? In fact, it knows about it in a very nice way. I motivated the Schwarzschild AdS solution for you as a one parameter family of solutions the other day. I said there's a horizon size, which tells you what which is proportional to temperature for large black holes, and that's one parameter in the solution. But once we go to the planar solution that we have here, what the black hole does is that it breaks Lorentz boost because by picking an inertial frame, along which you see the temperature. So the time direction has been singled out because the energy non-trivial energy density in the thermal state. But you could pick some other reference frame by boosting yourself with respect to the plasma. So I claim that the Schwarzschild AdS D+1 geometry should be really viewed as a d-parameter family of solutions, one prescribed by d-1 boosts and one temperature. And I package the boosts into a single normalized time-like vector u mu. And here is a covariant way of writing it, boundary covariant way of writing the metric from before. This is just still in the ingoing coordinates. If you took u mu dx mu to be dv, this is my previous solution. But now I've just decided that instead of talking about dv, I'm rotating the vector one form dv in the boundary directions by boosting it. This guy is dual to a plasma, which is homogeneous. With energy momentum, which is of the perfect fluid form. But the energy density and pressure are simply given by the from the free energy. They just obtained from thermodynamics from the free energy. But now you can try doing something interesting. You can take this solution and you can ask, what if I don't care about this global equilibrium where the energy density and pressure are homogeneous in the plasma, but make them inhomogeneous by allowing them to vary in space and time? Well, I can do that if I make these parameters of my original solution u, and the horizon size is buried in this function f, functions of the boundary coordinates x. Your immediate reaction is, well, fine, you can do that, but you won't solve equations because the equations will only get solved when u and r plus are constants. That's true, but I can now try to correct the solution by adding other terms to compensate for the fact that u and r plus are not constants anymore. Okay. If I allow u mu and r plus to be general functions, all bets are off because I still don't have any anchor points. But if I allow them to be functions which vary slowly, and this so that they're slow gradients, motivated by the fact that I'm trying to extract modes that are supported at low energies and low frequencies and low momentum. So I'll try to do a gradient expansion. And what's remarkable is that Einstein's equations can then be solved order by order in gradient expansion, completely analytically, and you can extract out the bulk metric and the boundary stress tensor explicitly. Just to say, what one ends up doing is one ends up solving the Einstein's equation with both components along the boundary and the Hamiltonian and the radial Hamiltonian constraint, but one never solves the boundary equations, which are just the conservation equations of the energy momentum tensor. What one obtains in this context is a one-point function of the energy momentum tensor as a functional of u mu and r plus, whose conservation imposes the remainder of the Einstein equations. So what you get is an off-shell fluid data, which you have to then put on shell by solving the fluid dynamical equations. So this has been called the fluid gravity correspondence because what it tells you is that there's a way to repackage a subset of Einstein's equations, namely the momentum constraint equations of gravity in AdS, into conservation equations for a stress tensor with the stress tensor precisely parameterized by a fluid dynamical form. Okay, and this was worked out to 2 orders in derivatives. I've just written out the leading piece, which is the ideal fluid part, and the shear tensor contribution sigma mu nu is a transverse traceless symmetrized derivative of the velocity. And this coefficient is related to my diffusion constant. And in fact, it directly gives you the shear viscosity of the n=4 plasma. There are many interesting statements that came out of this discussion. One which I wanted to highlight, which is that it gave us important insight into.
I have a question.
Please go ahead.
So this so this T mean U, this is on the boundary, right?
This is on the boundary, yes.
All right.
Yeah, so I'm in this case, I've been only solving vacuum Einstein's equations with negative cosmological constant to get an ideal fluid, because I'm only focusing on energy momentum dynamics. But if you put matter and studied anything, again, you would get like we were doing yesterday, you would get the boundary stress tensor and boundary webs for fields, other operators. Anything else, folks? Okay. What I was going to say was that it gave us important insight into contributions from Toft anomalies in fluid dynamics. Both for flavor and Lorentz anomalies to relativistic fluid dynamics. Okay. So this is one place where this inflow discussion that I had a couple of days ago was important. Because from the inflow, one can actually understand how. So what usually one does when one studies anomalies in quantum field theory is one understands how anomalies show up in the vacuum correlation functions. You draw some triangle diagrams and you see how the current is not conserved in the presence of sources. Something remarkable is that when you have a current which has anomalies, there are additional contributions that survive even in the absence of sources and give you anomalous transport. And those anomalous transports were first cleanly understood from this holographic context. Okay, so that's what I wanted to say about the general discussion of constructing nonlinear solutions. Of course, as you can appreciate, I only focus on a subset of solutions. One can start going to town because supergravity has lots of fields. You can write down solutions with many fields. We can have gauge fields and other scalar fields and so on and so forth. And you can construct many interesting geometries and study them and their interpretations in field theories, as various people have done for various applications over the years. Any questions about this? I take 5 minutes. Thank you. Okay, if not, I'll end on this slide, which is setting up the discussion for understanding how geometry might arise from field theory. This is not the full story, but this is a sort of the 0th order entry into the dictionary. So all we've discussed so far was that the way I think about the correspondence is that we started from somewhere. We started from string theory, and we got told by analyzing configurations in string theory that there is an intrinsically deep correspondence between the dynamics of closed strings in AdS5 in AdS geometries and that of some boundary field theory on the boundary of the space. Some field theory that you can think of as living on the boundary of the spacetime. What is not clear is, suppose you were a field theorist and started out by asking yourself the following question: okay, I'm told there's this duality. What must I do in the field theory to see the geometry. What observables in the field theory must I use to build geometry out of? And there have been many discussions of this, and some of the upcoming lectures will talk to this in greater detail than I will. But I promised Neta that I will say a few words about the extrapolate dictionary and what bulk reconstruction could mean. So here goes. When we looked at the Lorentzian areas geometries, we found that in contrast to the Euclidean problem, we had normalizable source-free solutions. So we could have solutions which behaved the field value in the bulk when suitably scaled out with the power of r to the delta. R is now 1 over z. I'm using global coordinates. Gave me the boundary operator. Really, when I said it before, I put a web here, but now I'm removing the web and thinking of what's called the extrapolate dictionary, that the boundary limit of the bulk field with power stripped off is the boundary operator. Since it's purely normalizable, I can invert this logic and say I can write the bulk field as an integral transform with some Green's function of the boundary operator. Okay, so this guy is called the Hkl Kernel after Hamilton, Cabot, Lifshitz, and Lowe, who first went through explicit constructions of this, although the discussion of this particular integral transform dates back to discussions by Bank, Douglas, Horowitz, and Martinek in the late 90s. And now, depending on what kind of Green's function you pick, you could reconstruct you could either do what's called global reconstruction. So you could talk about operators, any bulk fields anywhere here, but then you would have to reconstruct them in terms of a entire patch of the boundary that sits in this on the cylinder over some finite length of global time. Or you could do local reconstruction within the causal wedge of a given boundary region and just talk about operators that are stuck within the causal wedge. So both of these are understood in terms of some class of bulk operators, in terms of some kernels. The kernels are explicitly only known for the vacuum geometry because it's easy to solve the wave equation, but you can imagine writing down kernels of this kind for any bulk spacetime. So when I talked about this AdS soliton, where you had some, sorry, not the AdS soliton, some solitonic geometry with some excitations in the bulk, you could still imagine that there is a map between boundary operators and bulk fields with the kernel carrying state dependent information for that corresponding state. What has become clear in the last decade is that this is not the full story. You can reconstruct. So this would be a statement of reconstruction because this would be trying to build from field theory data with some information that comes from the state, a bulk object that rightly has every right to be called a field operator at this point. But you could imagine doing a lot more than asking this question, which is, and what we've started to understand and what you will hear about in upcoming lectures is, first of all, that this is limited because one can first of all reconstruct a larger domain of the space-time, namely the entanglement wedge, which I haven't defined, and the mechanics of how that is done needs input from quantum information aspects of AdS CFT. So on that note, I think I will stop, which is a good place for the next set of lecturers to take on from and show you what we understand about AdS CFT in more modern parlance.
Excellent, thank you. So questions from anyone? Just to remind you, we will have a Q&A session in half an hour anyway, but if you want to ask something while the just pertaining to this particular end of the lecture, then now would still be a good time to do it. Okay, well, if not, then, oh, William, are you, okay, you have your hand up? Go ahead and ask.
Yeah, just going back towards the beginning of the lecture, you mentioned these phase transitions of the black hole. Yeah, that slide there is great. I just was wondering, you said that sometimes you can get, or essentially that these minimal surfaces are not unique necessarily. Do you ever get any sort of geometrical frustration effect that occurs from degenerate surfaces?
We don't get frustration from degenerate surfaces, but what you do find is, given, at least the examples I know of are ones where you have surfaces that sort of do this. They wrap around the horizon multiple times. They sort of bend back, come back out. So they sort of fold back and forth on themselves. Do these kind of funny things. But no, so in some sense, you might call that geometric frustration because there's some frustration preventing it from accessing this side. But
Okay.
maybe you have something else in mind.
No, I just, I guess I was drawing a perhaps inappropriate parallel to the type of behavior that you can get in certain condensed matter systems when you can't have a preferred lowest energy, or in this case, minimal area surface, not a unique minimal area surface.
Oh, but so usually the examples I know where you get degeneracies, they are isolated points in the parameter space. Let's say for sizes of the region relative to the boundary size, it's an isolated point. You don't get something over some domains.
Okay, thank you.
One could add one more thing, that the surfaces don't interfere with each other in any way to frustrate them.
Yeah.
So,
Could I ask a question?
go ahead.
Good.
It's about the last slide that you had. So in this equation that you wrote down, the extrapolate dictionary, I'm used to thinking of the operator O in the CFT as an operator. So it's not something that's number valued, but the left-hand side is a field, which I'm used to thinking of just as a number. So, and if I want to make a number out of the operator O, I would have to do something like take the expectation value in some state. So how do I make sense of this equality then, where the left-hand side seems to be a different mathematical object than the right-hand side?
Good. I think you should think of this also as a bulk quantum field.
Okay. Sorry, go ahead.
No, go ahead.
I was just, so far we haven't been thinking of it as a quantum field, right? We've been doing classical field theory in the bulk.
That's
but
right.
Now we're going a step further, or is this like a different interpretation from what we were doing before?
No, I would say that the limit we were studying for the large part of the discussion was to pretend that we could understand the bulk for the purpose of doing certain computations. We could treat the bulk fields as classical. But they're truly quantum objects because, as I said, there's a hierarchy of approximations we made, starting from a string path integral to quantum gravity path integral to classical gravity. But genuinely, these guys, they would create and annihilate particles. Even in fact, let's say, how would we think about this? When I said we should think of single particle states which would be created by the creation and annihilation operators of phi in the bulk as single trace, as corresponding to single trace operator states in the boundary. I really would have to say that you take O as a quantum operator on the boundary and you create a state, but in the bulk that would correspond to inserting one creation operator of phi. so that the corresponding field just propagates out in some wave packet. We've just been sort of eliding over that in so far as our bulk of our discussion, but at the back of my mind, I certainly have been thinking of phi as classical limits of quantum fields. So we're not adding anything more to the discussion, in a sense of speaking.
Okay, I think maybe my problem is in the way that I learned quantum field theory. I never really learned how to make contact between a quantum field and the classical field. They seem like, I don't see the way that I can think of a limit of a quantum field as becoming a classical field. So I've always been a little bit confused about this. I don't know if you have an answer to that. Or if the question makes sense.
I understand what you're asking.
Like a quantum field is something even in the free field case where I have creation and annihilation operators. A classical field seems like something completely different. It's just a function on space-time. And with a quantum field, you have states and you have a whole bunch of stuff, but in a classical field, you don't have any of that.
Yes.
Maybe there's a different way in which the correspondence of going from quantum to classical makes more sense rather than that operator formalism. But I was wondering if you could explain this maybe.
Okay, let me try.
It's not a very clear question, so if not, that's okay.
No, I understand what the concern of the question is, but I'll try to see if I can explain it in a meaningful way. So I agree with you that the passage from quantum to classical in general is complicated, even for single particle quantum mechanics. And there are many different ways you might think about it. You say harmonic oscillator, I have discrete energy eigenlevels. And you might want to say high up on the spectrum, it looks mostly the energy eigenvalue, eigenstates look mostly classical, but that's not quite accurate because you can ask questions that are not answered by the classical description of the harmonic oscillator. It's just that once you start sampling over a large part of the Hilbert space and sort of smearing over things, that things start looking classical too. So in single particle quantum mechanics, one way to approach this is to look at distribution functions in the classical phase space sense. Think of Wigner distributions or things like that, and try to ask how do the quantum probability distributions map back to classical probability distributions. If I'm asking an analog of that in quantum field theory, I actually don't know how to make that work. I mean, I haven't tried making it work, but I also don't know if in place where I've seen it made worked out. But my answer would be, in analogy with quantum mechanical stuff, we say, if you make a single particle wave packet of the field phi as a quantum field in the bulk, that would correspond to creating a single state. But a sharply collimated wave packet of phi should be thought of, if it has support in some small window, should be suitably thought of in a distributional sense as a quantum creation operator with appropriate uncertainties.
Okay. I guess ultimately, I didn't intend my question to be so fundamental. I was just, in the GKPW dictionary, we think of phi as a strictly classical thing, at least in the saddle point approximation.
True.
And in this dictionary, it's clearly an operator. So I guess it's maybe the distinction between thinking of the operator formalism and the path integral formalism.
In this discussion, certainly yes, because to make phi the classical field, we are taking some saddle point value of a quantum operator.
Okay.
Yeah.
Thank you.
Can I ask a question about this?
Yeah.
So it seems to me that in order to build up your HKL dictionary, need to have a background metric which is classic, right? So you need a classic geometry, and you solve your equations of motion for the field, and you build up your Hkl. And you were also saying that you basically treat phi as a quantum field in the bulk. So my question was, where is the threshold where you can actually do this, and when the quantum fluctuations of the phi field become too relevant and back react on the geometry, and so the whole construction blows up? Is it still related to the limit you were talking the other day about, where you have the central charge scaling as n squared? So as long as you don't have many particle states in the bulk, you can still not react on the metric, and so you're able to build your HKLL, or is there any other caveat on that?
No, it's exactly that, because as Sergio points out in this chat, related to Petra's question, this phi should be thought of as a saddle point value of a quantum field in the limit. That's what it really is, the path integral language. And what we're saying is that the saddle, as long as the saddle point is valid, we can sort of study excitations on top of the saddle point, and those will be the few particle states or order n particle states, but really we can't touch order n squared particle states with this dictionary. I mean, we can, but we have to cheat a bit, because then you have to modify this kernel. You have to change the kernel to account for the change in the state. It's a matter of, to a certain extent, it's a matter of bookkeeping, because as you pile in more and more bulk particles and they start back reacting, then the geometry changes, and likewise this kernel changes. But there should be a map. So in some sense, it's like, in string theory, inserting vertex operators, and you want to exponentiate those vertex operators at the end of the day if you want to have a coherent state background. So again, these are words, okay? So I don't think any of us have ever sat down and worked this out and sort of said, here's how it works. But I think that's, morally speaking, how it should work.
Sorry, so can I clarify, in this operator equation?
Yeah.
This isn't strictly an operator equation, because you can't take any state and act on the left-hand side and get the thing on the right-hand side acting on that state. You can only do that for states that are close to the geometry which you're using to calculate the propagator K.
Correct.
Okay.
Correct.
And in the next weeks, you'll hear the words code subspace that will clarify a bit of this.
Hi. Regarding the fluid gravity correspondence, in here you were very much like expanding around the Schwarzschild AdS. Do you have similar like fluid gravity correspondences if you expand around different solutions?
As long as
can you still do this
with,
kind of gradient?
yes. So as long as you have an equilibrium starting point, you can do this. So typically, the expansion has been carried out in the neighborhood of starting with any equilibrium black hole solution, which could have carry a lot of charges and so on. Other charges, maybe have, this is AdS, so you can have solutions with scalar hair and so on and so forth. And yes, one can definitely expand around that and construct analogous solutions. I just did it for the simplest case where you don't have any additional fields floating around. So my equations are pretty simple. But there were interesting discussions for.
Mm-hmm. Do you need the solution to be static or is stationary enough?
Stationary is sufficient. I just need some notion of equilibrium and some way to sort of track small flux deviations from thereof.
Okay, thank you.
Okay, so if there are no other short questions, we can thank Mukund again.
Can I ask a quick question?
Okay, go ahead.
Sorry. So if you go back to your minimal surface slide, so you talked about this discontinuity, the jump in minimal surfaces when the black hole goes through the Hawking page transition. So I was wondering, since if I'm looking at a black hole in AdS and if I'm tracking its information with time, then if I'm looking at it from the minimal surface side, should we see this jump when the black hole goes to the highest point in the page curve?
So sorry, I said something which I think might have misled you. I said here that this transition between this disconnected surface and this surface, this pair of surfaces, that is like a Hawking page transition.
Okay.
It's okay. Now, what you're asking is, suppose, and I didn't, in this discussion, I tried not to look at the same region at different times, which we can also do, which is what you're asking. So we can certainly look at the following question. You fix a region and you monitor how much entropy is there in that region. Or if you're interested in these page curve type discussions, you could fix the entire CFT and monitor whether you're getting all the information out. So we could imagine the following experiment, which is you sort of start with a gas of radiation, which collapses, forms a black hole, and evaporates away. And 20 years ago, some of us would have told you, oh, look, there's a boundary field theory. The boundary field theory is unitary, ergo bulk gravitational collapse followed by Hawking evaporation must be unitary. And the sort of question would have been, but how? Yeah, how does it manage to do that? What has been understood now is at least this page curve discussion, which is a good proxy for seeing how that unitarity is restored, how the purity of the system is being seen as a function of time. And what's happening in that context, which I'm sure the people coming up will talk about, but let me say in the context of this discussion, as someone pointed out, you will have, let's say, a surface of this kind, which is the thing that increases along the page curve for some amount of time. Okay. As you sort of compute the density operator now, you compute the density operator 1 unit of time later, 2 units of time later, there'll be some simple surface that you just compute, and its entropy, its area will keep increasing, and the entropy will keep increasing. After some time, which nicely happens when you use the quantum extremal surface generalization of this, including the contribution from islands and so on, what happens is you get a new saddle point. A new solution. There's a new solution to this problem, which starts to become comparable in area. And in fact, remember that there's always this business about taking the minimal area. In fact, I claim that if you use this fact that the formulae of holographic entanglement entropy formulae always want you to take the global minimum in the space of extremal surfaces, quantum or otherwise, basically always tells you that purity has to be restored, because you sort of go up, you hit a maximum, but then if you have a new saddle which has a smaller area, you have to pick that guy. And that's actually how it works in field theory. If you take a finite quantum system and you start looking at it by taking bigger and bigger chunks of the quantum system, as Paige pointed out, once you know more than half the system, then your 1 entropy starts going back down. Okay, so but you're morally speaking right that the discussion that Jeff Pennington and then Almeri, Marolf, Engelhardt, and Maxwell gave was pointing out that after the page time, there is contribution from new surfaces, which have smaller net area, which therefore bring down the page curve to restore unitarity.
Okay, thank you.
Maybe let me just add one quick thing to this. In the classical context, there's, I mean, different concepts that one used the phrase, phase transition in. One was this jump of just these probe extremal surfaces on a fixed geometry. So you have a fixed state and you probe it by looking at different subregions. And the other context, in the context of Hawking page, was really changing the state. So they're really changing the geometry. Those two
You're not changing the state.
Well, you're changing
the same thermal state. It's changing the geometry.
It's changing the geometry. It's changing the geometry from something that's pure AdS to something that has this black hole. And then you're not asking about what you're probing it with. So the transition isn't in the probe surfaces, but rather in the geometry itself. So maybe that I just want to add that word of clarification.
Yeah. So actually, Veronica makes an important point, because I can say what I meant here. That this jump between surfaces, which looks like a jump in the surface in the same geometry as she was saying, if you compute it by computing Rayleigh entropies, it is a change of geometries. Just that in the limit n goes to 1, because of the formulae, they just are surfaces in the same geometry. Yeah, that's an important distinction.
Okay, so we have we have 10 minutes. Then you can keep asking questions for another hour and 15 minutes. So let's take a break so that you survive for the whole hour and 15.